look at question number 6. In question 6, we are being assessed on how to identify if a function is exponential or linear given a table. Okay, so question 6 reads, the function f is shown in the table below. So this is f of x and this is x right here. And question, which type of function best models the given data? Is it exponential growth, exponential decay, linear function with positive rate of change, or linear function with negative rate of change? Okay, so if we're given a table, how do we know if it's one of the following? Let's go ahead and indicate exactly how to identify each of these types of functions given a table. Okay, so the first one, an exponential growth function. In that case, the growth process will be as follows. It will involve multiplying by a constant. So you multiply by a constant. That's the common factor, okay, or the growth factor. You multiply by a constant. Let's call that constant r, and that constant is always going to be greater than 1. Okay, so if you're multiplying by a constant, the same number over again, and it's that number is greater than 1, it will generate an exponential growth function. How about decay? It's similar, but a slight difference. In this case, you're going to multiply again. You're going to multiply by the same number over and over again. Multiply by a constant. This is a decay factor in this case. But that r factor will meet the following condition. That r, or that constant or decay factor, is always going to be between 0 and 1. For example, if you have an r value of 1/2, you're going to have an exponential decay function. If you keep multiplying by 1/2 over and over and over again, you have an exponential decay function. How about linear function with positive rate of change? If you have a linear function, you're going to be adding, is an additive process. Okay, you're going to be adding a positive number for a positive rate of change. So you're going to add a constant. Let's call that constant m, and that number that you're going to be adding over and over again will be greater than 0. Okay, if you add the same positive number over and over again, you end up with a linear function with positive rate of change. How about linear function with a negative rate of change? In this case, you're going to add a constant again, but guess what? The constant is going to be negative. Okay, so let's call that constant m. Is going to be negative. All right, think about a negative slope of a line. That's the deal here. So if you add in a negative number repeatedly, is equivalent to subtracting that number over and over again. Alrighty. Now another thing that can help us with this problem is to note the behavior of the function. Okay, what do I mean by behavior? So in the exponential scenario, if you have growth, what does that tell you is going to be happening with the function? If you have a growth scenario, that basically tells you that the function is going to be increasing. Alright, the behavior is it's going to be going up. How about positive rate of change? Positive rate of change tells you the behavior also. This is a scenario where the function will be increasing also. Alrighty. Now, what about decay and negative rate of change? Decay basically indicates that the function is going to be decreasing. That's what decay does, right? The amount is going to be reducing. So decay means it's going to be decreasing. And a negative rate of change basically means you have a negative slope. What do you know about lines with negative slope? They're decreasing, okay? So just by considering the behavior alone, you should be able to eliminate options. What am I talking about? Now take a look at f of x. As x increases, what is happening with f of x? 1, 3, 9, 27. It's increasing. Okay? So since f of x is an increasing function, it tells us that we can eliminate option 2 and 4, since those two functions exhibit a decreasing behavior. Alright, now the growth factor or rate of change can tell us how if it's linear or exponential. Alrighty, so let's take a look at it. Now let's act like we don't know what the answer is, all right? So we're going to look at this. So if we go from 1 to 3, it's two possible things that are happening here. Either you add 2, okay, 1 plus 2 is 3, or you multiply by 3, all right? Now, if what we're adding is the same constantly, then it's going to be a linear function with positive rate of change. If it's not, then it cannot be a linear function. If what we're multiplying is the same, is a constant, then it's going to automatically be an exponential growth function. All right, so let's see. If you go from 9 to 7, from 3 to 9, that's an addition of what? Addition of 6. Oh dear. We're not adding a constant. This is variable, so it cannot be a linear function with positive rate of change. So the answer is automatically option 1. Okay? All right, but let's go ahead and show the whole process. So from 3 to 9 is equivalent to multiplying by 3. And then from 9 to 7, to go from 9 to 7, you add 18, right? You see how this is changing? So we see it's not linear. Or from 9 to 3, multiply by 3. Ladies and gentlemen, I hope you clearly see what the answer is. What's happening here is that we're multiplying by a constant that is greater than 1. Okay? Alright, so let's write that down. So what's the deal here? When you multiply by a constant that is greater than 1, what kind of function is it? Greater than 1. So you constantly multiply by that constant greater than 1. It tells you that it is an exponential growth function. It's an exponential growth function. So the answer to question number 6 is option 1. Okay? Alright, so how would you rate the level of complexity of this problem? 1 meaning extremely easy, 10 means extremely difficult. How easy was it for you to solve this problem? Give your rating. 1 easy, 10 means extremely difficult in the comment section below, and tell us why you think the level of difficulty corresponds to the number that you assigned to